Good. This is period 3. We are in lecture 12 of calculus. Let us begin. We're going to quickly go over some homework problems, then we're going to talk about some new stuff. So, there was this homework problem number 84, even problem, very exciting. It gave you these two functions written in this exact way, and it asked you to differentiate them and then notice something cool. So I will do it the lame way. The lame way is to just be seduced by the book's representation of the function and tricked into doing a quotient rule. Let's do that. The derivative of this is the derivative of the top, so that's cosine x minus 3 times the derivative of the top times the bottom minus the top times the derivative of the bottom, which is 1 all over the bottom squared. And when I do this, I get x cosine x minus 3x minus sine x plus 3x all over x squared. And that turns into just being x cosine x minus sine x over x squared. Good so far?
Yeah.
All right. So over here, then, we take the derivative of g. We get the derivative of the top. Cosine x. Wait. Derivative of the top, cosine x plus 2 times the bottom minus the top times the derivative of the bottom all over the bottom squared. And I think something similar happens here now, right? We get x cosine x plus 2x minus sine x minus 2x all over x squared. And that is, interestingly, also x cosine x minus sine x over x squared. I cannot help but notice that these derivatives are the same. What is the significance of this fact? Please explain this at all possible levels. Kellen?
Their slope is the same.
Their slope is the same.
I mean, the tangent line to it, the slope is the same.
The slope of the tangent lines to the curve are the same. Yeah. Jimmy?
You can before he's showing you
Okay, wait, yeah. So wait, but following up on Kellen, I guess I'll just follow up myself. Not when you just say the slope is the same, it just doesn't make it sound quite as dramatic as saying that the slope is the same for every single x, right? In other words, when the derivative formulas are the same, that means that for any possible x which I plug into this derivative, I'm going to get the same thing back. So in other words, their slopes are always the same. That means that the rate at which these two functions are increasing is exactly the same for every single x. More, Richard.
So they must be pretty much the same function.
They must be pretty much the same function, Liam.
They're just shifted along the y-axis.
Yeah, is that what you were going to say? Yeah, Liam says, well, I'm not quite, look, ready, I can give you a function f, which is, x squared plus 5, and I can give you a different function g, which is x squared minus 8, and these two functions are going to have the same derivative, right? In fact, I like to think of the derivative. The derivative is the function which is telling you what to do, right? The derivative is like the coach, who says, do this now. Like what are those sports where the coach is like really mean and tells you like exactly what to do? Yeah, like swimming or like
insanity.
Dodgeball? No coach in dodgeball. Something like swimming or like diving or gymnastics or something like that, right? Where every little tiny motion that you're making, the coach is telling you, do this, do this, do this, do this. And the derivative is telling you what to do. So if these two functions have the same derivatives, like they have the same coach, telling you exactly what to do at every single second. And so one person might start here with their dive and might be being told by the coach to, go up. Okay, now go down. Okay, now go back up again, right? And if this other person has the same coach, then they're going to do the exact same things at the exact same time. In other words, they're going to change in the exact same way. And what you have are like, synchronized swimmers or like synchronized divers or whatever, basically, right? Liam and Aditi's observations are correct. If two functions, it's obvious that if two functions are vertical translations of each other, that they have the same derivative, right? What's less obvious, but also true and very deep and a little bit difficult to prove, is that which is what they were saying, is that if two functions have the same derivative, then they must be vertical translations of each other. That is also true, but that's difficult to prove. Yes?
Could they be phase shifted? Like,
no, because if they're phase shifted, then for a particular x value, they might be doing different things,
well,
right?
phase shift like 2 pi.
I mean, if it's periodic, then yes, but if, generally speaking, if you shift, then it's not going to be the case if they're doing the same thing at the same time. Okay, good, that was a problem. And then there was a Richard made some, was it Richard or someone else made some algebra, it was you, made some algebraic observation. Yeah, so actually the cool way to do this problem is to not do what I did. The cool way to do this problem is to look at f and to first simplify the numerator and just write this as sine x over x minus 3, and g is just sine x over x plus 2. Ha-ha! Of course they are going to have the same derivative now, because they are literally basically just the same function, just one's 5 more than the other. Follow? All right. 103. 103 is this function g of x, and g of x is e to the x over x. Okay. Let's talk about this function. Oh, what are you supposed to do? Find the second derivative, right?
Yeah.
Okay, so there's a bunch of different ways to do this. Personally, I don't like the quotient rule. I find it kind of like annoying. So I'm going to write this as e to the x times x to the negative 1, because I just find that a lot easier. And now I'll proceed towards the... What?
Yeah.
Yeah. In retrospect, yeah. So anyway, basically you just do it. When you do it, you get the derivative of the first, which is e to the x, times the second, plus the first times the derivative of the second, so that's negative x to the negative 2. And now I will simply differentiate again. So g double prime of x, well now I'm differentiating this, well that's just the same as what I had before, right? So actually I can pretty much just copy that. The derivative of this is, according to the product rule, e to the x times x to the negative 1. So the derivative plus, or rather I'll just write minus e to the x times x to the negative 2. And now I have to differentiate this, which is, again, according to the product rule, the derivative of the first times the second plus the first times the derivative of the second, which then becomes 2x to the negative 3. I think I did that correctly. And, okay, look, I could just stop here, but have you guys noticed that the book does a lot of algebraic simplification, post-differentiation? Have you noticed that? Yeah, that is because the book is trying to push a particular agenda, which is to get you to not just differentiate, but to also to write it in a nice algebraic form afterward. Okay, so I think you should do that also. Sorry, let's just do it now. So, okay, I have a name for this. It's a little bit R-rated. Are you guys ready for this?
Oh, gee.
Sometimes I get shy. So, differentiation is like sex.
Oh.
The algebraic simplification afterward is like the pillow talk. Both are important. The pillow talk is a very important part of the overall experience. You can't just differentiate and then just get up and leave the room. Sometimes you have to stay for a while and to make sure that your derivative is comfortable and that you've finished everything that you need to do there. Alright? So that's what we're going to do now. And we can do all kinds of things like combine like terms and factor out e to the x. So factor out e to the x, we get x to the negative 1 minus 2x to the negative 2 plus 2x to the negative 3. Oh, I'm not done yet. We can write this, we can do some algebra and write this out without negative exponents, which I think is a good idea. So that's 1 over x minus 2 over x squared plus 2 over x cubed. And that can also be simplified as e to the x. Let's see, that becomes x squared minus 2x plus 2 all over x cubed. That is nice and beautiful and simple and great. Why might we be so concerned with simplifying the derivative afterward? Yeah, Jimmy.
Because you might want to use it as a function, or like you might want to have them use it.
Yeah, he says that we might want to use it. This particular unit that we're in is actually, even though it's kind of awesome, is one of the least sort of thinking units, because we're not really doing anything with the derivative. You notice that we're more or less just taking the derivative and then just moving on to the next problem. In fact, this entire unit is just learning how to differentiate everything. But what might, can you guys maybe look ahead a little bit and see, what might I want to get out of this derivative? You kind of already know some things that are lurking in the background that I've mentioned a little bit here and there, but not so much. What's one thing you could just do with the derivative? You could graph it, yeah, but what does the derivative tell you? Slope, velocity, acceleration, all these things are true. How about just one thing? How about when the derivative is 0? Seems kind of important. So when the derivative is 0, that means there's a horizontal tangent. Have you guys noticed anything yet about like horizontal tangents? No? Maybe you just move on. If you haven't noticed it, then I don't want to rush you. All right, well, there are some things. I mean, if I just draw a curve.
Oh, it's changing direction.
Yeah, Will says, and I think a couple others said it too, it seems to be the case, by the way, this is not a proof, this is not anything, this is going to all come later, but it at least seems to be, I think this is the first time we've mentioned this, but it seems to be from your curve sketching activity as well, and also just common sense, that when there is a horizontal tangent, there's going to be like a relative min and max. And those seem like really important things that you might want to know about a function. And this is actually one of the great things that you can do with differentiation. So there are often times in the next unit when I will not just be taking the derivative, but I will also be taking the derivative and finding out, for example, when it's 0. Because when the derivative is 0, I learned some important things about the function. Cool? Okay. Good. That was 103. Let's do one more, which is like 139. 139, going very fast, is the following function. Oh, actually, they just give you a quadratic, ax squared plus bx plus c, and then they tell you a bunch of information. They tell you that the graph has a tangent line with slope 10 at the point 27, and an x-intercept of 1, 0. Okay, x-intercept 1, 0, and slope with, so slope with, or slope of 10 at 2, 7. Okay, so in a tricky way, they have just given you a bunch of pieces of information which are then sufficient to, you're moving the camera and stuff, right? To determine what A, B, and C are. First off, by just telling me that the x-intercept is 1, 0, that means that f of 1 has to be 0. So f of 1 is in fact just A plus B plus C, and that has to be 0, right? Okay, so that's one equation right there, bam. But the other thing they tell me is that when the slope is 10, or there is a slope of 10 at the point 27. Well, just by saying that there is a point 27 at all means I can plug into getting 4a plus 2b plus c, and that has to be 7. Bam, that's 2 equations out of 3. And then it's also true that the derivative of this function is 2ax plus b, and I know that when the slope of the tangent line is 10 at the point 27, then I know that f prime of 2 must be 10. And f prime of 2 is, according to my formula, 4a plus b, and so I have that 4a plus b has to be 10. And now I have a system of 3 equations in 3 variables, and it's easy to solve. Probably like the fast way is to not do a matrix or anything, just like do it.
Just like plug in 4a plus b into the 4a plus 2b.
Oh, that works too. Here, to me, this just seemed really fast. Because you just upside down subtract these two, we get 3a plus b equals 7. Yeah. And then if you also have the 4a plus b equals 10, then you can just upside down subtract again, a equals 3. That was pretty fast. A is 3, b has to be -2. Did I do that right? I'm trying to show off now. Yep. And then C has to be -1. Bam, done. Okay, can I have this homework? So where are all other people at your table? Oh, you're scared of the video camera? Good. Can I have this homework? Now we will do something awesome.
What are you doing?
Can you raise the
Why
bar?
do you do these things?
Or somebody?
Never mind now.
We gotta flip the camera here. Okay. For you.
No dogs in the chair. Not sitting in this chair.
All right. Time to have some deep talk. Are you ready?
I need some paper so I can write down the detail. I have paper.
Let me collect my thoughts. All right. Let's do one of those things again, where we talk about all the things that we know how to differentiate and all the things that we don't know how to differentiate. What do we know how to differentiate?
E to the X.
Yeah. I know the derivative of e to the x. I know
Polynomial.
all polynomials, so just like polynomials. Sine, cosine, yeah, so can I just write all trig functions? Because I know sine, cosine, I know the six basic trig functions at least. So maybe all is a little bit of an exaggeration, but all of the 6 basic trig functions I can differentiate. Polynomials, e to the x. 1 over stuff, yeah, so x to the n when n is anything positive or negative. And we've kind of been cheating and we've been pretending that we know it for other things too. But I'll just write when n is an integer and not 0. Although we've been cheating with like x to the 1/3 and stuff. Yeah, later.
Reciprocals.
Yeah, reciprocal. So yeah, and by that I guess you mean any function that I know how to differentiate. I can also differentiate its reciprocal. Yeah.
Quotients and products.
Yeah, products, quotients, quotients, sums of 2 functions. So if I know how to differentiate 2 functions, I can differentiate their sum, their product, their quotient, their reciprocal. Is that everything?
Constants.
Constants, although that's like a subset of polynomials. And then the one we learned last class, natural log. That's pretty much what we got. All right. What's left? Yeah.
Functions nested inside other functions.
Yeah, functions nested inside other functions. Yeah,
We don't know how to do that.
we definitely don't know how to do that yet. So there are, I'll use the technical term, not nested, but in fact, what's it called? Like,
Piecewise.
No.
Oh,
no,
fail.
not piece-wise. Don't mean piece-wise. I mean,
Composite.
yeah, composite, exactly, composite functions. So I do not know how to do things like the sine of x cubed, or perhaps, so I don't know how to do this. I don't know how to do things like, e to the cosine x. I don't know how to do things. Let's do this. And I think someone actually, was it you that brought this up last class? Someone brought this up in some class. Anyway, no, maybe it was a different person. Yeah. All right. So, what should I do next? Yeah. All right. So let's maybe start with an example. So so let's take our function. Let's take a function f which is sine. So we know how to differentiate sine. That is
Cosine.
it is cosine. And that's pretty exciting. And so since that's f prime, thank you. And for example, f prime of 0, once I've proven this rule, is just guaranteed to be 1. Thank you, Griffin, again. And we understand this on some geometric level. In fact, we first conjectured and proved this fact, and we used that to prove whether the derivative was cosine in general. And recall that the significance of that was you know, that since sine kind of looks like this, then what this is telling me is that the slope of the tangent line at the origin is 1, right? And it looks like 1, so that's all good. Okay. Well, now we're going to do some just exploration, conjecture, and et cetera, common sense and things. So I'll now give you a new function, g, and this new function is sine 2x. One of those functions nested inside functions situations, composite functions. What do you think the derivative of g is? Don't answer. Use all possible means at your disposal, although I think I'm partial to drawing a picture of sine 2x and maybe using your sketching derivative skills, conjecture what you think the derivative of sine 2x should be. Don't call it out.
Draw a picture. Don't just blindly guess. You could? Yeah. But maybe more learning would happen if you drew sine 2x.
It's not tall. Oh wait, no, it's not taller. It's just like this. No, but if sine is 3, wouldn't this still be 2? Wait, isn't that 2 sine?
Yeah, that's 2 sine. Yeah.
That never happened. All right. Good. Good thing we're not recording this or anything. So, what is the actual correct answer, or the correct method? So now the period is pi, right?
Yeah.
I swear, I know now. So it's like this, right? Yeah. And then whatever. Okay. So, good. So, what do we think the derivative is? Well, okay. I mean, a couple of these, I guess, are pretty easy, right? I suppose that would be pi over 4 now, right? The derivative must be 0. At 3 pi over 4, the derivative is 0. What do we think the derivative is at 0? Yeah, I think it's 2. Yeah, you guys are pretty smart, plus common sense, plus like whatever. Yeah, it kind of has to be 2 because it's doing everything twice as fast, right? Even though we're still going back and forth between -1 and 1, we're doing it in half the time because we've compressed the function horizontally by a factor of 2. So it's got to go pretty fast to get from -pi over 4 all the way back up to 1 at pi over 4. And so I think the slope of this is 2, and that's just totally correct. And I could probably even do a limit if I wanted to prove that. And then the slope at pi over 2, yeah, then -2. And so I guess, and then at pi it's going to be 2 again. So I'm looking at something kind of like that, right? So based on this, just based on my intuition, guesswork, sketching, thinking, what do we think the derivative is? acting like a cosine curve. It also has period pi. The derivative is going to repeat every pi since sine 2x is repeating every pi, but everything's happening kind of twice as fast. So yeah, I think that this is 2 cosine 2x. Do you all agree?
Yeah.
Okay, and then other people, including Ali Anwar, had another way of solving this. I bet it's occurred to at least like half of you, because you're like, you know, trained to know things about these functions. Ali Anwar.
You could just use the double angle formula and then product rule.
Yeah, that's exactly correct, right? So we could rewrite sine 2x as 2 sine x cosine x, and then we could apply product rule. Product rule says that the derivative of this is the derivative of the first, which would be 2 cosine, derivative of the first times the second, plus the first times the derivative of the second. The derivative of cosine is negative sine x. And so what I end up with is 2 times cosine squared x minus sine squared x. Recognize that?
Yeah.
It is 2 cosine 2x. So indeed, we have just proved via algebra techniques that our intuition is confirmed. All right. So this is the subject of today. The subject of today is how to treat this problem in general. We were able, because this function is on the inside here, it's not too complicated, it's just the double me kind of function, then we could make a picture and we could see. So I don't know, is this surprising to some of you maybe that it works? I don't know. It was too late. I should have asked you, I should have just made the whole class just shout out what you think the derivative of sine 2x is and wonder and then see what happened, but it's too late now. So yeah, in general, I need some kind of process for differentiating these functions. And if we sort of start to even sort of think about this, the derivative of sine 2x, well, it's kind of like cosine 2x, but then there's this 2 appears as a sort of a correction factor, you might say, or something like that. The correction factor is a 2, well, I don't know. More about this in a minute. All right, and actually, even before we begin this, I'm gonna do this lesson in a particularly weird kind of way, in which I sort of just give out the answer in advance. But not quite yet. First, I want to talk a little bit about notation. Have you guys noticed? I warned you that this would happen, but also maybe you weren't. Even though you were warned, it was still a shock that there's just like so many different notations floating around for differentiation. Let's take this seriously for a moment. When I write this sort of dx notation, this kind of means take the derivative of whatever's in the inside, right? This is sort of like the differentiation operator, you might say. This is convenient in certain cases. Well, that's one thing that we do. What we normally do is we say things like f of x equals x cubed, and then we have this sort of prime notation in which we say then the derivative of this function is 3x squared. All right, but so that's one way of doing things. But sometimes, and if you notice, what I did here is that I named this function. I named this function f first, and then I differentiated it. This notation is convenient when I just don't even care enough about the function to particularly stop and give it a name. So I can just say things like, what is the derivative of 3x squared? Nope. Further mistakes happening. What I meant to say was, what is the derivative of x cubed? 3x squared. Do you see how this is the exact same thing as above, but now I just don't name the function? Latham, can you keep an eye on the video camera? Because we have like tall boys in the front, so if they're in the way, just like whisper and tell them to slap more.
The only one in the shot is him.
Okay. All right. Good. Yet there is even another way of what's up? There is even another way of talking about this function, which also comes up in the book, which is y equals x cubed. And this is something that you might have done a lot of in Algebra 1, and then we sort of beat it out of you a little bit. Because what's interesting about y equals x cubed is I'm sort of not using function notation here, so I'm sort of being a little bit informal. I'm saying, hey, here's the rule for y. Y is just the cube of x. But I am it's a little subtle what's going on here, is I'm not explicitly referencing that y is a function of x. I'm simply saying, hey man, here are these two variables, and they're related in this kind of way. And have you noticed, the book does this, but I don't think I've done this yet. They say that then dy dx is 3x squared. Has the book done that yet? feel like they have, right? Okay. So this has a name. This is called the Leibniz notation. And I think that's what it's called. The Leibniz notation is actually really awesome, and I'd like you to sort of feel really comfortable with it. The Leibniz notation, and the way we read it, we pronounce this. The way that we pronounce this is we just say, dy dx. No one says dy over dx. People just say dy dx, and then we expect them to know what that means. And this kind of says, do you guys sort of like, why is that sort of good notation in a certain, so maybe give you the opportunity to say so, yeah.
If you have something that's not and you can also talk about different variables if you have more than just two.
Yeah, that's a big one. But even before I get to that, yeah. Were you going to say something?
Well, you could put like functions in each of them. Like you could put a function for
Oh,
x.
yeah, but no one ever does that. No one ever does that. So what is this actually? Why is this kind of good notation for the derivative specifically? Well,
Because y and dx like respectively represent infinitesimally small like differences in y and x. You have infinitely accurate slope, which is like the exact slope.
yeah, everything he's saying is amazing. Yes, that is good. Let's not forget what the derivative is. The derivative is it's supposed to be the slope of the tangent line, and it all comes from the secant line. So it's like we have some function, and we want to know what the derivative is at a certain point, like x. And what do? We go over to x plus h, and we put points here, and then we make the secant line. And when we make a secant line, we have this quantity and this quantity. This is the change in x, and we use delta x for that. And this is the change in y. And so there's something going on here, right? Slope is the change in y over the change in x. That's what slope means. And so since a derivative just really is a slope, then this dy dx notation is really nice because it sort of reminds me that a derivative is a slope. And just like Will was saying, delta y is an actual change in y, and delta x is an actual change in x, whereas dy and dx are sort of meant to remind you of like an infinitesimal change in y and an infinitesimal change in x. And in fact, one way then, using this notation, I could say dy dx, which is the derivative. By the way, we treat this thing as an entire symbol in and of itself. Okay, so this is not a fraction. Even though it looks like a fraction, it's not a fraction. It's like some things can't be broken up further into their component parts, right? Like oh, I heard that. So can't think of an example suddenly. Like the word what? Kitchen or something, right? That's just a word. It means kitchen. You can't just break it up into like kitchen. It doesn't make any sense. What? What? This is the worst example I ever thought of in the entire world. Just take someone's name.